lesson 14, we're going to graph factored polynomials. And like I was saying at this point, you really, really need to have a graphing calculator. And if you're planning on going to college, which you probably are, you're going to need one for that. So it wouldn't be money wasted to purchase one. Also, in the library, remember, you can rent one. The low cost of $10. You just need to go down there, get a form, have your parent or guardian sign that form, bring them the $10, and they check one out to you. It's going to be the same kind as I'm teaching you guys with this TI-84 software. So let's go to it. All right, so this problem has an engineer designing a roller coaster for younger children. I don't know why. If we look at the graph of the roller coaster, it looks terrifying. So I don't think you want to put your younger child on it. But anyways, it's a function that models that during the first 300 yards. Right, so h of x models that for the first 300 yards, where the roller coaster is 100x yards from the beginning. So for instance, right, when x equals 1, we're at 100 yards away, when x equals 2, we're at 200 yards away, and so on, right? So that's what's going on with this thing. So the first question asks us, does this function describe a roller coaster that would be fun to ride? Explain. And we could go through this thing, right? We could set up a table of values, x and y, and we could plug in different values and graph it by hand just by plotting points and getting an idea for it. But just for the sake of time and for the sake of getting us used to our technology, let's go ahead and graph this thing using our graphing calculator. So you'll go to your graphing calculator, and you're going to hit the y equals button, and that's going to get you to this page. And then at that point, you're going to enter. First of all, make sure for your leading coefficient, if it's negative, don't use this minus sign. Use that negative button. Okay? Use the minus sign, it'll tell you there's a syntax error. You need to use the negative button. Now after that, if you're saying like 4x minus 3, you're going to use the minus. Anyhow, so we're going to put minus 3x to the 4th power. Don't forget to hit this arrow button to get out of the exponent. Plus 21x to the 3rd power minus 48x squared. And then we have plus 36x. So there it is. All right, now that I have the function entered into my calculator, I'm going to just hit graph. And a terrifying looking roller coaster should appear. Would you put your child on that? Yeah. So to answer that question, does it look like a roller coaster that would be fun to ride? I would say yes. It has a huge drop. It has a big drop. All right, so let's write that. And that's really all I care about is the drop. All the other stuff is cool, but I love a big drop. All right. Can we see any obvious x values from the equation where the roller coaster is at height 0? Well, let's look at it. So indeed, there are some obvious x values right here. We have the coordinates 0, 0. Right over here we have the coordinates 2, 0. And over here we have the coordinates 3, 0. So in other words, we have x-intercepts at x equals 0, at x equals 2, and at x equals 3. So those are our x-intercepts of the graph. And we're going to find those algebraically later. So to answer the question, we would say yes. At x equals 0, x equals 2, and at x equals 3. So we have already used a graphing utility to graph the function h. And now to put it into context, when is the roller coaster 0 yards off the ground? Well, it is 0 yards off the ground when x equals 0, x equals 2, and x equals 3, right? Right, this function gives us x in yards away from beginning, and it outputs h of x, which is yards away from the ground. All right. So what do the x values you found in part C mean in terms of distance from the beginning of the ride? And remember, it says that the distance from the beginning of the yard is 100 times x, right? So 100 yards for every unit increase in x, which means that x equals 0. Well, that's the beginning of the ride, so it's not very informative. But at x equals 2, at x equals 2, that's going to be 200 yards, and at x equals 3, that would be 300 yards from the beginning of the ride. And then there's a random question in there involving some physics, but not really having much to do with the actual math we're doing here, right? They put the largest cell first because momentum, right? All right. Moving right along. Okay, so we are going to factor the polynomial h, and this one is interesting. So we have that h of x is equal to negative 3x to the 4th power plus 21x to the 3rd minus 48x squared plus 36x. All right, so we just learned how to factor by grouping. If I see something that has 4 terms in it, that's immediately what I think of. But remember, the first thing we need to do when we're factoring is see if we have a group of greatest common factor, or if each one of these terms has a greatest common factor. So, indeed, this one does. 3, right? 3x, rather. Yeah, 3x divides each one of these terms evenly. And I really don't like that negative sign out in the front of my leading coefficient. So I'm going to go ahead and factor out a negative 3x. Okay, so that's going to give me negative 3x to the 4th divided by 3x to the 4th is going to be x to the 3rd power. And then this will give me negative 7x squared. This one, negative 16x. And over here, this will be, my bad, positive, right? Because I factored out a negative. So what that's going to do is change the sign of everything inside of my parentheses. And we'll have negative, right? 36x divided by negative 3x is going to give me negative 12. Okay. So now that I've factored out my greatest common factor, I'm thinking, hey, let's factor by grouping, right? Because that's just what my instinct tells me. Since I have those 4 terms there. So I will factor this group. Out of this group, the greatest common factor is going to be x squared, right? So I'll factor the x squared out, and I went with x minus 7. And you can see that that's true if I was to distribute the x squared back in. And then the greatest common factor over here looks to be 4. So I will factor out a 4, and I wind up with 4x minus 3, and that's no good. Yeah. So this fails factoring by grouping, right? if I was going to factor by grouping, I need these two binomials to be the same so that I can factor them out. So I cannot use any factoring methods that we've learned so far to actually factor this. So I'm going to have to get tricky. So this is actually not helpful. It's not untrue. It's just not helpful. All right. So this is what I'm going to do. I'm going to go back to my graph. And I'm going to say, okay, I have zeros at x equals 0, which is right because this right here tells me that one of my solutions, if I was to set this thing equal to 0, one of my solutions would be x equals 0, right? Because of this 3x that I factored out. Okay, well then if that's true, right, and we see that this x equals 0 is here, then isn't it a case that because of this x equals 3, x minus 3 should be a factor of it, right? If 3 is a 0 of this particular polynomial function, then it must be the case that it's divisible by x minus 3, right? It's another way of saying that it's a factor, that x minus 3 is a factor of it. And you'll see it. It'll all come to light when we try to divide. So let's see if we can get something out of dividing this thing. So in other words, what I want to do is figure out what is 3x to the 4 plus 21x cubed minus 48x squared plus 36x, whoa, 366. I want to know what happens when I do that. Well, the good news is synthetic division is always there for me. And I apologize, actually. I'm going to want to use the factored version of this. Sorry. Oh. I want to actually, because what's going to happen is we already decided that there was this factor 3x, negative 3x, right? I'm looking for a factor within x cubed minus 7x squared plus 16x minus 12. There we go. Let's do that one instead. Because I mean, it would be fine if I could divide the other one, but then I'm gonna have to factor the 3x out again, right? All right, so let's divide this. We'll use our synthetic division because it's faster. All right, so 3 times 1 gives me 3, negative 4, then I get negative 12, then I get 4, then I get 12, and 0 is my remainder. That's fantastic. So that means that this is x squared minus 4x plus 4. Okay, now we've gotten somewhere. So what does that mean? That means that I can factor this thing. That means that this is equivalent to negative 3x times x minus 3 times x squared minus 4x plus 4. Beautiful. It's true, right? If I was to multiply, if I was to distribute this this back in, right, I would wind up with this guy, right? Okay, but that's not all. There's more. If you act now, you can factor this using, it is indeed a perfect square trinomial, right? I'm going to go ahead and actually, and now we have cleverly, ever so cleverly factored this. It was no simple task. And have we verified the zeros from our graph? Indeed, we have. We pointed out earlier that we have this x equals 0. And then there's also the case that x equals 3 and x equals 2. So those are our zeros or our x-intercepts. also could be called solutions, right? If we were to set that equal to 0. Fantastic, we did it. How do we think that the engineer came up with the function for this model? He put random young children on a roller coaster and decided how tall it needed to be. No. He probably decided the intervals at which he wanted that thing to reach the ground, right? And then possibly came up with this factored form, right? He probably looked at the zeros. If there was indeed an actual engineer involved. So, hey, what's wrong with this roller coaster model at distance 0 yards and 300 yards? So let's look at it. At 0 yards, I mean, have you ever seen a roller coaster that rose that quickly? And furthermore, this thing actually has like a shape like that. Of course, it's much steeper, but roller coasters don't go up that way, do they? They go up like that, right? So there's a problem. It starts off pretty much going like very close to vertically. And if I was on a roller coaster like that, it'd be like, what did I sign up for? In an excited and happy way. But all right. And then what's the problem at x equals 3? I believe the roller coaster just slammed into the ground. I mean, yeah, it should probably end like that, not by slamming into the ground. So, all of the young children have perished. That's not good. That's not good. I'm going to say maybe a lawsuit, but maybe. All right. And I don't know if we really need to write that down. It was a good discussion to have. Okay, so let's go ahead and do some graphing. Oh, here we go. So the first thing I want to do is I would really like to have an x-axis and a y-axis. All right. Because this function is already factored, I know what my zeros are quite readily, right? I know because of the, and I'm going to write this over here, just so I can point some stuff out. So I know that x equals 0 is one of my solutions. Also, because of this one, I know that x equals 1 is a 0. I'm sorry, an x-intercept, right? And right here, I know that x equals -1 is also going to be one of my zeros. So I'm going to go ahead and put those points on my graph. -1 and 1. All right. So we know that it crosses the x-axis at these points, but like, what does it do on either side of them? We just don't know yet. So there are two things that we could do. We could plug in different values into this function and figure out what it's doing in between, say, in between 1 and 0, and in between 0 and -1. But that's a little bit weird for this function. So let's just go ahead and go to our handy-dandy graphing calculator and get a look at it. And we'll be analyzing these in depth. Let me get rid of this stuff. So let's hit that y equals. Hey, if you ever want this thing to go away, all you got to do is push the clear button. And let's graph something different. Here we go. X, our function that we have is x times x minus 1, and then x plus 1. Not that. All right, so I hit my graph button, and then we get a look at this thing. Hey, look at that. it's a cubic, and we'll discover as we go on that all cubics that have a positive leading coefficient will follow approximately this shape. So here we go. So now we know approximately what these things look like. It's actually going to be a little bit challenging to fit on our little graph here, but we're going to make it happen. So it doesn't quite reach y equals 1, right? And then it comes back down and it doesn't quite reach y equals negative 1. And then it comes back up. And I'm just going to write these arrows to signify that this thing keeps going on and on and on and on forever and ever and ever, right? In the direction of negative infinity and in the direction of positive infinity, right? It just keeps going out like that. Right, and as it approaches negative infinity in the x direction, it will also approach negative infinity in the y direction. As it approaches positive infinity in the x direction, it will approach positive infinity also in the y direction. All right, so let's do the next one. Hey, isn't this the same thing as x plus 3 to the 4th power? Okay. So that means that this thing is a 4th degree black belt? No, polynomial. And it turns out that second degree polynomials, right, quadratics, all behave in the same way, right? They look parabolic. All third degree polynomials look a lot like the one that we just graphed. There will be different variations if the coefficient, the leading coefficient is negative. Same with this one. 4th degree polynomials. All of them with a leading coefficient that is positive will look a lot like this one. So we're starting to see an overall general picture of what these things look like. Here we go. First thing I need to max these. There we go. I know that this thing intercepts the x-axis, right? It has an x-intercept at x equals negative 3, right? Because that's a 0. So that's about all that thing tells me about this thing so far, right? I know where it crosses the x-axis. That's about it. I can multiply it out and find the y-intercept pretty easily as well. No?
Well, not that you can see.
Not that you can see on your graph, but it turns out that your y-intercept should be about 3 to the 4th power. Because when you multiply this thing out, so if you were to do your distribution, right, on this particular thing, so if you were to distribute, right, boom, 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 right, just how we know that it's a 4th degree polynomial because, sorry, I meant to point that at an x. So we know it's a 4th degree polynomial because I have x times x times x times x, right? I also will be able to know what my y-intercept is. And we'll get into this a little more because I know that I have 3 times 3 times 3 times 3, right? So I have 3 to the 4th power somewhere in that when I expand it, right? We'll get into that. We'll get into that in more detail later, right? Turns out that when x equals 0, y is going to be 3 to the 4th power. We'll explain that in more detail as we go. For now, hey, let's look at this thing. Let's graph it using our graphing utility. So we have x minus 3, right? Or was it plus 3? Thank you. Not divided. Here we go. To the and there it is. If we were to zoom in on this thing, we'll see that it's not actually flat right there at x equals 3. It actually is curved. If it was flat, it would have a bunch of x-intercepts, and that would be really strange, right? So it's not quite flat. And you can zoom in on a point and look at it. And we'll do stuff like that as we go on. But for now, let's get a general graph. So it kind of looks like, wow, not like that. That's for sure. Something like that. Sorry, but I don't draw well. So it looks like a parabola, and it should look like a parabola, but it's not quite a parabola because it is not quadratic. It is quartic. Okay. Moving right along, let's do that again. That was so fun. Ooh, lots of zeros. So I'm going to rewrite this just because I have this x plus 4 has a multiplicity of 2. So I'll rewrite this as f of x equals, I'm going to run out of room over there. That's fancy. Okay. X minus 1 times x minus 2 times x plus 3 times x plus 4 squared. I will draw my x and my y axes. All right, so we know from this that we have solutions x equals 1, positive 1, right? We have x equals 2. We have x equals negative 3. And we have x equals 4. What does that mean? That means that the graph of this particular polynomial has x-intercepts at x equals 1, x equals 2, x equals negative 3, and at x equals, sorry about that, negative 4. All right, so the only way that we could go about figuring out what's in between of those without a graphing calculator, right, would be to create a table of values, right? If we plug in some x, it would output some y. It would actually just plot all the points, and it would put together the picture for us. It would take a really long time. It's really worth doing, but for right now, we just want to get a general idea of what these things are. We want to see them. So let's go ahead and let the technology help us out with that. So let's go ahead and go to our handy-dandy calculator. So let's go ahead and graph this thing using our graphing utility. Negative 1, negative 2, 3, 4. So you go to y equals. If you've got something in there, hit clear. Okay, so let's put this thing in there. So I have x minus 1 times x minus 2 times x plus 3 That would be x plus 3. And we have x plus 4 squared. Oh, brother. That's better. Is that it? Yeah. X minus 1. X minus 2. X plus 3. And I hit graph. And there we go. So we're going to have to zoom out on this thing a little bit just to kind of see a little more. We'll just assume it goes way up and way down, right? Between the x-intercepts -3 and +1. It is extremely positive. And between the x-intercepts +1 and +2, it is going to be extremely negative. Let's draw a sketch of that. Look at it one more time. Okay. So it's going to come up from the negative direction, across the x-axis, or I believe possibly even just touch the x-axis at that point. And then it comes back down. And how far down does it go? 1, 2, 3, 4, around y equals -4. Y equals -4. I'm going to have to make that a little more drastic. Darn it, I erased too much, but that's okay. Here we go. So we're going to go. Comes back up. And then it goes super, 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 super positive. So possibly much higher than that, probably. And then it will come back down across the x-axis. And then it goes very, very negative in between these 2 points. We're not exactly sure how far, but definitely more than 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 units. And so it's going to go way lower than that, come back up. And then what does it do after that? It looks like it just continues on as x approaches positive infinity, y approaches positive infinity, right? There we go. Something like that. Of course, this turning point, or this relative maximum and this relative minimum are not going to be exact. And that brings us to a discussion about that, right? So on our graph, any place where we have a turn, right, where the graph goes from moving in the positive y direction to the negative y direction, we call that a relative maximum. Any point where we have the graph, the y values of the graph turning from decreasing, right? They're becoming more and more negative, to increasing, becoming more and more positive. We call that a relative minimum. And so on. So we have a relative min here. We have a relative max here. Yes.
So relative maximum is the point before it starts to go down?
is the point where it changes from increasing to decreasing.
So now more.
Absolutely. There can definitely be. All right. So real quick, let's look at what the degree of this polynomial is, because I think that's a very important thing to know. And we're going to look at how many x values do we have in here. We have 1, 2, 3, and we'll count this one twice, right? So 1, 2, 3, 4, 5. So this is a 5th degree polynomial. There we go. All right, ready to do it again? Let's do it again. Okay. Once again, I'm going to draw my axes. And I'm going to decide that I have x-intercepts. Well, so first of all, I know that the easy ones are at 2 and at 3, right? But then I have this going on, and I got to see, hey, is that an intercept, right? So I will subtract 1 from both sides. Then I'll take the square root of both sides, and I wind up with this weirdness that your calculator, if you punch that in your calculator will say, no, it does not have the button like on the game taboo. It does not go. It actually tells you that this is a non-real solution. Okay, so it'll tell you non-real. So that's not real. So that means that this thing has only 2 intercepts at x equals 2. All right, so we have another x-intercept at x equals 3. And there's something going on all around those things. We're not sure what. Let's go ahead and put this into our handy-dandy graphing calculator. So I'll go to my y equals. I'm going to clear that thing. And I have inside of my parentheses x squared plus 1 times x minus 3 and x minus 2. All right, let's graph it. Ooh, pretty. All right. Let's go ahead and graph that thing. Okay, let's put this thing in there. So I know that it's got this drop right here, and it drops around to y equals -2. So that's really the only thing I need to know. I know there's an inflection point, right, where it's kind of changing direction a little bit up here. And that's occurring around y equals 4. So good, we can make a fairly accurate sketch of this now. So it goes way up and then around y equals 4, it has this inflection point. Something like that. Right, and then I said it drops down to almost y equals 2 and then comes back up. And there it is. That's one of the best drawings I've ever made.
I know, this one's good job, Armin.
Thanks, guys. All right. So let's go ahead and move on to the next one. Where we're going to do... Gonna do a bit of algebra on this now. Alright, let's use the fact that x minus 4 is a factor of x to factor this polynomial. Alright, well, what did we do before when we knew that we had something that was a factor? What do we do? We divided. We divided. So they haven't given us much room, have they? For dividing. But that's okay, because I'd like to use synthetic division. Alright, so I'll put a 4 here. And then that's a 1, a negative 13, a 44, and a negative 32. 32. Alright, 4 times 1 is 4, and then we get negative 9, negative 36, and then we get 8, and then I would really like that to be negative. What did I do wrong? Well, that's a negative 32, there we go. So that's 32, and that's 0, and that's what I really wanted. I needed to have there being absolutely no remainder. So, what happens? Now I know that this thing is actually, I factored it using division. So that means that I've got x minus 4 times, right, this right here stands for an x squared. So x squared minus 9x plus 8. And then it turns out that what I could do is, well, is that factorable? Are there two? Yes, indeed, there are two numbers there. If I multiply them together, I'm going to get positive 8. But if I add them, I'll get negative 9. And those are going to be negative 8 and negative 1. All right. So we factored it. That's awesome. So our x-intercepts are going to be x. Right, x equals 4, x equals 8, and x equals 1. It's a good day for that. And then at which x values can the function change from being positive to negative, or from negative to positive? Okay, so how are we going to know where it's going to change? Well, we can plug in some numbers. Alright, so if we had no graphing calculator in front of us, what we'd have to do is get out our maths, right? So I know that this thing crosses the x-axis at 1, 4, and 8, right? We're going to go consecutively. So I'd like to know, what's it doing between, say, 0 and 1? What happens if I plug, so what is, theoretically, what's f of 1/2? Well, we can plug that in there. Well, we could also look at this factored version, right? So if I plug 1/2 into this factored version here, right, I'm going to wind up with a negative, right? If I plug the 1/2 in here, I'll wind up with a negative. And if I plug it in here, I'll wind up with a negative. So f of 1/2 is going to turn out to be a negative times a negative times a negative, which is going to be, we know that it's going to have a negative value. Alright? How about what's going on in between 1 and 4? So in other words, what about f of 3? Well, if I plug negative 3 in here for the x minus 4, I'm going to end up with a negative times a negative. Right? If I plug it into the x minus 8, and then if I plug it into the x minus 1, I wind up with a positive. So I've got a negative times a negative times a positive, which is going to wind up being positive. Alright, so now let's look at what goes on in between x equals 4 and x equals 8. So, I don't know, say f of 6. And you can go ahead and plug these all into your calculator and get real numbers. It's alright. It'd be the best thing to do. I'm doing it shorthand right now. F of 6. Well, if I plug 6 into x minus 4, I get a positive. If I plug 6 into x minus 8, I get a negative. And if I plug it into x minus 1, I get a positive, so that means I'm going to wind up with a negative. And then lastly, let's look at something greater. Let's look at f of 9, right? So I'll look at what's going on above x equals 8. F of 9 is going to be positive, right? Alright, let's use our technology to connect that all together. Let's go ahead and graph this thing. Alright, so look at that. It all matches. Did I make a typo? I did. Alright. So it's moving from negative to positive. Alright, as it crosses x equals 1, and then between x equals 1 and so we have positive values, right? And then it's changing as it goes through. I have the actual paper in front of me, so you'll see that it matches, right? So that'd be one way to interpret that. All right. So that's what we've just done. We've considered whether the function is positive or negative on those 4 intervals. Look at that. Got them. We did it already. That's foresight for you. Alright? How do we tell if it's positive or interval or negative on an interval? Well, we just did this. Simply. So we pretty much just did all of this. Let's point right there. Look, we did all that work. Okay? So for x greater than 1, is the graph above or below the x-axis? Well, the way that we could tell it's both above and below the x-axis. They didn't give me an interval. Weird. Because above 1, right? F of 3 is positive, right? F of 6 is negative. So for x is greater than 1, or sorry, my bad. I'm not reading correctly. X less than 1. For x is less than 1, it appears to be negative, right? So it is below. Sorry, because f of 1/2 turned out to be negative, right? Had a hard time reading there. Look at that. I learned how to read when I was a young wallaby. Alright, for the interval from x being between 1 and 4, is it above or below? Well, we determined that f of 6 was negative, so it is below. Alright? Okay? Well, it looks like you're going to have to do a little more. We've already done this as well, haven't we? So we could use this information to graph it. Here we go. Alright, so we've already answered h and I by plugging in certain values. So let's go ahead and sketch this. So I'm just going to rewrite the function here because that's helpful. I'm going to write in its factor form, right? So f of x was equal to x minus 4 times x minus 8 times x minus 1. Right. So we got an x-intercept at 4 and at 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? 1, 2, 3, 4, 5, 6, 7, 8. Oh, that's in the right place. And then we got an x-intercept here at 1. Alright. So, we have said that at f of 0 we're negative. So it should be down here. Let's go ahead and look at a graph on my handy dandy graphing calculator. And there it is. Let's graph that thing. So it's very negative, and then it increases. It is, and then it goes way up here. It's not accurate how far it goes up. And it goes quite far down as well. Not quite accurate that it's going to turn right there. And there it is. And we can see that that matches our values that we found from plugging in some numbers. And we've just done K. So fantastic. There we go. There's some very, very important stuff that we need to discuss, all right? We're able to determine how many relative maxima or minima there are based on the degree of each polynomial, all right? So the degree of this polynomial is 2. This one is 3. This one has a degree of 4. 1, 2, 3, 4. How many x-intercepts? 2 x-intercepts. This one has 3 x-intercepts. And this one has 1, 2, 3, 4 x-intercepts. The number of relative maxima or minima. This has 1 relative minimum. This one has 2. It has a relative max. And it has a relative minimum. This one has 3. There's our min. Here we have a max. And here we have a minimum. Alright, so let's see. What observations can we make about this information? It looks like a second degree polynomial should have at most 2 x-intercepts and 1 minimum or maximum. A third degree polynomial should have at most 3 x-intercepts and 2 relative maxima or minimum. And we can conclude the same thing about a fourth degree, right? I say at most because, right, because of what we're having go on here, right? There is no x-intercept for this one, right? There's no x-intercepts. So that's why I say at most, right? This particular one has only one x-intercept, but we would expect, since this is a third degree polynomial, right? We have 1, 2, 3. Right? If we were to multiply that out, we would wind up with an x to the third. But we would expect this to have 2 x-intercepts, right? And it actually has a 0 relative max or min, right? We cannot say that this is a min. This is actually an inflection point. Or a point where it changes direction. It's changing direction, but it's not going from from increasing to decreasing. Across this, it is still increasing. It never stops increasing. So we call that an inflection point. And we'll see that the same rule doesn't hold true. So that is what I said at most when we were defining those other ones. And that's what they're trying to get you to get from this information. All right. Well, that was all. Thank you so much for watching. Hope you have a good day. Because it's a good day for a good day.